In this video, we're going to be discussing relationships between unit weight, porosity, and moisture content. So to get started, I want us to consider a soil mass. And so we're going to go ahead and draw it in the form of a phase diagram, just like we've been doing in the past. And of course, we're going to have air, water, and solids, okay? Now on the weight side, we remember that the weight of air is negligible, so we're not really going to show that. And we are going to show, however, the weight of water and the weight of soil solids. And then, of course, total weight is just the sum of those two. So that's total weight W. And then on the volume side, we are going to have a volume of air, volume of water, and if we combine those two, what do we get? Volume of voids. And then down here, of course, we have volume of solids. And then our total volume is just V right here, okay? So to get this started, again, we're trying to create some relationships between unit weight, porosity, and moisture content. So the first thing we're going to do is we're going to say, let's consider total volume equal to 1, okay? Now that could be 1 cubic meter, that could be 1 cubic foot. It's just a unit volume. And notice that in this particular illustration, we're taking total volume equal to 1, not volume of solids equal to 1, okay? And remember, we discussed in class that we can assume pretty much any one single value is equal to a unit, a unit value. But depending on what we're trying to calculate or show, it may be more convenient to express one thing as one or the other. So in the past, we've taken volume of solids as 1. Now we're going to take total volume as 1 for what I'm trying to show here. So the first thing I want us to recall is the definition of porosity. So maybe take a second, think about that, pause the video, and remind yourself, what is porosity? Well, that is equal to the volume of voids over the total volume. So the reason why I'm saying let's consider the total volume equal to 1 is because, again, I'm trying to build relationships between unit weight and porosity with moisture content. So porosity has total volume in the denominator. So in this particular illustration and exercise, it's most convenient to take the total volume equal to 1. So if total volume equals 1, then what do we have? I'm going to draw a little arrow here. We're going to say the volume of voids is just equal to the porosity, right? So in my phase diagram, I can start populating that. I can say total volume equals 1, all right? And my volume of voids just equals the porosity. What about the volume of solids? Well, clearly then, the volume of solids is equal to what? Well, it's total volume minus the volume of voids. So the volume of solids is equal to 1 minus porosity. So I can put that in my phase diagram right now as well. 1 minus porosity, which is eta, okay? So what do we do now? Well, let's relate the volume side of this phase diagram to the weight side. And if you remember from last class, we talked about this quite a bit. We also did a numerical example. How do we relate volume to weight? Well, we would use unit weight. And the same idea would go as if we had mass instead of weight, we would use density. But since we're dealing with weight, we're going to relate volume and weight through unit weight. So let's make a note of that. Relate volume and weight by unit weight, and we call unit weight gamma, okay? So let's do that. Let's look at the solids first. How about we say specific gravity of soil solids is the unit weight of soil solids divided by the unit weight of water. And then what's the definition of unit weight of soil solids? Maybe pause the video and remind yourself. Unit weight of soil solids is weight of solids divided by the volume of solids, okay? And then I'm just going to keep gamma water down there in the denominator. So I can do a little bit of rearranging, right? How can I do some rearranging? Well, do I know an expression for volume of solids? Yeah, we have volume of solids equals 1 minus porosity. So watch what I can do now. I can say this is equal to the weight of solids divided by, instead of volume of solids, I'm going to say 1 minus porosity, right? And then all that's divided by unit weight of water. So now what kind of relationship can I establish? I can say now G sub S equals weight of solids divided by unit weight of water times 1 minus porosity. And of course, I can do a little bit of rearranging. And at this point, it's just algebra. I can say the weight of solids is equal to G sub S gamma water times 1 minus porosity. Now, this right here is a handy little formula to keep in your back pocket. So, so you want to make sure you kind of box that in or put a star by it, okay? So what can we do now? Well, we can now it's going to be kind of hard for me to write that equation W sub S in the phase diagram. So I'll tell you what, how about I just put a little check mark right there by W sub S. What about some other terms? Can I establish some relationships for weight of water and total weight? Yeah, absolutely. So let's scroll on down a little bit. And we're going to say, I'm not going to show all the algebra here, but because the steps are pretty similar to what I just did. So I'm going to say, and the weight of water can be determined by moisture content times G sub S times unit weight of water times 1 minus porosity. And I'm going to say we can do that since the moisture content is equal to weight of water over weight of solids. So basically what I'm doing here is I'm taking the definition of moisture content, all right, and I am substituting that definition of moisture content, doing some rearranging into my weight of solids right here. So essentially I'm taking weight of solids and I'm rearranging the moisture content equation and I'm substituting it into this term right here, and then that gives me this weight of water term. So maybe on your own, do that little algebra step and convince yourself that this is true, okay? And then what we can say is, therefore, we can develop the following. Therefore, we have the following. We can say gamma dry will equal weight of solids over total volume. That's just the definition of gamma dry, nothing new there. But I can substitute that weight of solids term into my numerator, so I'll get G sub S gamma water times 1 minus porosity, all divided by my total volume, which was 1. Remember, we assumed that earlier. And then, of course, that's just G sub S gamma water times 1 minus porosity. Okay, so again, this becomes a handy formula for dry unit weight. Okay, so I can kind of write this all compact here. Okay, so maybe box this in. That's a handy little formula for dry unit weight. I can do a similar thing for total unit weight, right? Total unit weight is equal to total weight over total volume. And of course, total weight is weight of solids plus weight of water over total volume. And then likewise, I can substitute my two expressions in from earlier into weight of solids and weight of water, and do a little bit of algebraic manipulation. And again, I can end up with this handy little formula, G sub S gamma water times 1 minus porosity times 1 plus moisture content. Now, I didn't show all my algebra steps here, but there's a few algebra steps kind of embedded into this step here. So again, maybe take it upon yourself and convince yourself that that is true. That could be a good quiz or midterm exam question. So gamma equals G sub S gamma water 1 minus porosity times 1 plus moisture content. Okay, again, A good little midterm exam question could be to show the algebra that derives this equation, okay? And then continuing on, I can say gamma sat will equal gamma water times 1 minus, watch your parentheses here, 1 minus porosity times G sub S plus porosity. Again, there's some algebra embedded in there. And then I can say moisture content is expressed as porosity divided by 1 minus porosity times G sub S. Again, I didn't show all my algebra steps in the development of these equations, but take it upon yourself. Look into that. The textbook also has some information on these formula developments. So as we've mentioned before, these formulas are handy if you want to do some quick calculations. And if I tell you you can use them, then sure, you can use them. However, on other phase diagram problems where we have numerical values, if I tell you to use the basic ratio definitions, then that means I do not want you to use these formulas if I ask you to use the basic ratio definitions. But later on in this course and in the follow-up course, Foundation Design, you may find that these formulas are quite handy to use.